Materials for metals. Let's talk about metals, the structure of metals. Now, when we did electricity, you know, a metal is a regular arrangement of atoms or ions, if you like, in a sea of delocalized electrons. That's metallic bonding. Now, it's a bit more to it than that. Metals are polycrystalline. That's the best word to describe the structure of metals. They are polycrystalline. Poly means lots of little regions of crystallinity, lots of small regions of crystallinity called grains. And grains you can't see with the naked eye. You need a microscope. You need to burn the rubbish off the surface of the metal with an acid and look at it with a microscope. They're typically about 1/10 of a millimeter big, but there is a lot of variation. Metals are polycrystalline, okay? The properties of metals, different metals have different properties. A lot of it is to do with the size of the grains, the arrangement of the atoms within the grains. We don't need to know about face-centered cubic, body-centered cubic, basically how the atoms are organized, the size of the atoms, the strength of the bonds between the atoms, how many delocalized electrons there are, and something called dislocations, which I will talk about very shortly. An experiment you must do, force extension graph for a ductile metal, for example copper, stretching a copper wire, doing a force extension graph, and we get this graph here. There's two parts to the graph. There's elastic deformation, which is a straight line up to the elastic limit. Elastic deformation means it returns to its original length. After the elastic limit, there is plastic deformation, and plastic means permanent. It deforms permanently. What's actually going on at an atomic level, if you imagine all the atoms are joined by little springs, then in elastic deformation, we're just stretching the little springs, and when you let go, it returns again. With a ductile metal, in plastic deformation, what happens is that if the force is big enough, then the layers of atoms slide over each other and bonds are broken and then remade. Crystals slip. Yes, the layers of atoms slide over each other. They slip over each other. And that's what happens in a ductile metal in plastic deformation. Now, dislocations. A dislocation is an imperfection in the crystal lattice. There's various things can cause dislocations. It could be an impurity atom, which is bigger than all of the others. It could be an impurity which is smaller than the others, or it could just be a missing atom, a vacancy. But whatever causes this dislocation, it means that the crystal lattice isn't as lovely and perfect as it could be. Interestingly, a few dislocations may make the metal stronger and tougher, because it might make it harder for the layers to slide over each other. But if you have lots and lots of dislocations, then it may make it brittle, because the fact that the layers can slide over each other is what it makes it ductile, and that's what makes it tough. And if there's too many dislocations, then it becomes more of an amorphous structure, and it can become brittle. Something like pig iron, compared to wrought iron, pig iron. Or cast iron is very brittle as well.